Okay, so before announcing the next speaker, I have an announcement to make regarding the conference dinner on Thursday. So if you intend to go, please reply the message that you received until 2 o'clock this afternoon, because we need to make reservations. And when you reply, or if you had already replied and forgot to add, please let us know if you intend to bring someone with you. Just give the number of people, because we must make the reservations for the right number of people, okay? So if you haven't done that, please send a message telling the number of people, and we're waiting until 2 o'clock today for that, to make the reservations. Okay, so it's my pleasure to introduce the third speaker today, which is Ugo Bruzzo, from ICTP, CISA, and our own Universidade Federal da Paraíba. And he's going to talk on superschemes embedded into supergrassmannians. Okay, Ugo?
Thank you, Eduardo. Many thanks to all the organizers for this invitation. I'm very happy to be here in Rio once more. And as you can see, the title of my talk has two super in it. And actually, supergeometry is a kind of niche topic in algebraic geometry, but nevertheless, when I was to decide what to talk about today, I decided to take my chance and introduce some topic in supergeometry to this audience of algebraic geometry and commutative algebraists. Actually, I studied supergeometry many years ago. Then I stopped. Then I came back to it a few years ago due to my friend Daniel Hernandez Riperez. And actually, in the meantime, many years ago, I had morphed from a mathematical physicist, hopefully to an algebraic geometer. And so the work in the last few years, my work about supergeometry is within algebraic geometry. And the motivation of this, if you want to get some motivation from mathematical physics, is superstrings, where objects which are called supersymmetric curves, which generalize in a proper way the notion of a family of algebraic curves, is used. And also this, it has a natural generalization, which is the notion of stable or stable supermaps, perhaps, so leading to some supersymmetric generalization of, for instance, Gromov-Witten invariants and the like. So I thought perhaps I should spend 5 minutes on the, so to say, physical motivations, where, here physical should be physics, whatever should be written within quotation marks, because there's a huge discussion whether this has something to do with the world as we know it all. So it might be just another piece of mathematics simply done in a slightly different way, with less rigor and using techniques from physics. But anyway, whatever. So the physical foundations, or mathematical physics foundations, are from supersymmetry. So here I listed a few names. And just to give you perhaps the idea of what we are talking about, these are the equations. These equations are the so-called local infinitesimal supersymmetry transformations for a so-called hypermultiplet, which is made up by two scalar fields, so two functions, if you want, phi and f, and then a spin or chi, okay? Fermionic field meaning a spin, or so something which, as a field, carries a spinorial representation of say, the Lorentz group, or some orthogonal group if you work in a Euclidean signature. And so you see that well, in physics, so phi and f would represent particles that are called bosons, and the chi would be a fermion. And you can see that these transformations mix fermions and bosons, no? Because delta phi, the infinitesimal variation, depends on the fermion, etc. And if you want to, and what happens is that if you you can check that this Lagrangian, or better, the action functional associated with this Lagrangian, is invariant under this transformation. And here, epsilon is a point-dependent parameter. If you want really this Lagrangian to be invariant, this parameter must be anti-commuting. It cannot be a number in the usual sense. So the problem is how to give some sensible definition of what it is and construct some sensible mathematics on top of this very naive thing. And this, it originates then for supersymmetry. Then in some sense from supersymmetry, perhaps at least at the beginning, you could think that you take two different directions. One is purely algebraic. It generated the notion of superalgebra. You see, this is not a Lie algebra because this I represented here with this bracket is an anti-commutator. And so the P's are generators of translations, where the Q generates exactly the supersymmetries that are here in these equations. So they form what is called a Lie superalgebra. On the other hand, you may think that perhaps this has something to do with the geometry, where in addition to the usual coordinates, you have some odd coordinates, meaning that they somehow anti-commute, and this generates the notion of supermanifold. Why this is useful at all from the point of view of a physicist, for instance, what happens is that you can group the three fields that appeared in the supersymmetry transformation in a single field, but now on the space whose coordinates are both x and theta in this way. So you have just one scalar field, and this this contains everything. And this is actually very helpful in computations and the formulation of the theory. So end of this hand-waving part of my talk. So the idea is that, right, as I already said, to develop something sensible out of this. So we need a geometric framework where anti-commutative or fermionic variables appear, and this can be done basically in any category of geometric objects you like to consider. So you may like to work in the C-infinity category, you may like to work with varieties, algebraic varieties, I mean, with the superschemes, with the superstacks, whatever. And at the beginning, the very beginning, I'm talking about the late 70s, there were two different approaches, late 70s, early 80s. And what I'm going to use is the approach by two Russian physicist, Berezin, and the Russian mathematician, Esteves, and actually this day model prevailed. It's more elegant, more rigorous, it works much better, it's elegant, it's a sheaf theoretic, and indeed this can use to make supergeometry, so to say, in any of the categories that I mentioned. What happens is that, well, you do things at first, perhaps you, as always, when you start, everything is kind of easy, you can do many things, and then at some point you realize that you need really to be serious about this business, and you need basically, if you want to do algebraic geometry with this object, you really need to develop an analog of what we could call the foundations of algebraic geometry à la Grothendieck. So you need to deal with, at least with all the topics I listed here, right? This is kind of minimal amount of structure you need to do algebraic geometry in a proper way. In particular, and actually, this is not a casual list, but this is exactly what we have been doing over the last perhaps 4 years with Daniel and other collaborators. And in particular, what I'm going to talk about today was also done with Alexander Polishuk. And more recently, by the way, this paper in the meantime, the day before yesterday, was actually published in Advances in Mathematics, and we also did some work with Yuri Manin, who unfortunately passed away a month ago. And this is the part here about supercycle, super-Chow groups, leading to construction of a theory of stable supercurves, stable supermax, which is already contained in this preprint with Daniel and Manin, and perhaps with the idea of proceedings toward the supersymmetric generalization of Gromov-Witten invariants, for instance. So let's enter this world. And actually, this is the only equation, I think, in my slide, who's highlighted in red, because simple as it is really the key of everything, no? The base of everything. So we have this notion of a superring. So this is just a ring which is Z2 graded. But then it's not commutative, but satisfies this commutation rule among the homogeneous elements. When they are both odd, they anti-commute. Of course, a very easy model of this is a Grassmann algebra, right? The Grassmann algebra has immediately this kind of structure. And then we require some finiteness condition about the odd part, basically. So one considers the ideal J generated by the odd element. You want this to be finitely generated. Or equivalently, that the ideal is nilpotent and that J over J square is a finitely generated module over the quotient A over J. The quotient A equals fat A over J is just a commutative ring. And then the idea is that you just you may think, okay, let's play the usual game. Let's take the spectrum of this super ring, and of course you are led to consider Z2 homogeneous prime ideals. It happens, this happens to be the same as the spectrum of A. So you might say, okay, bad luck, we don't have anything in our hands. But actually what you do is after introducing the usual Zariski topology, you're thinking of this space as either the spectrum, superspectrum of the fat A or the usual spectrum of A. After doing that, you have, of course, as we know, to define a sheaf. But then you discover that if you define the sheaf just by localizing the superring, you obtain a much richer sheaf than the structural sheaf of the spectrum of usual A. So we have a kind of local model of superschemes, right? So just the spectrum of a superring, which happens to be an ordinary spectrum, but then we have this structured sheaf, which is a sheaf of superrings, which is naturally graded over Z2, and whose sections satisfy the anti-commuting property up there. Right? This is our basic object. As an example, you may immediately define the fine superspace of dimension Mn. So this pair of, the fact that the dimension is a pair of numbers is something that will be with us always. And so this is just the spectrum of the polynomial ring in all variables, even and odd, and with the structure sheaf defined above. And then you define locally ringed superspaces or superschemes as usual, right? They are locally ringed superspaces. Superschemes in particular are locally ringed superspaces that locally are affine. No? They are the superspectrum of a superring. And you know, for many things, life is not particularly exciting because you do a lot of work to prove things that sometimes hide subtle issues that you have to deal with. They appear because you are considering also these odd variables, but then you end up with the usual definitions and the usual relations among them. So it's not particularly exciting in a way, at least at the beginning. So you have the usual notion of a morphism of a superscheme. Perhaps we can just notice that if we give the obvious natural definition of what a morphism of superscheme is, you see, now a superscheme is always a pair where X is a scheme, and this O is this enriched structure sheaf that we have on top of it. And then there is a natural notion of a morphism of a superscheme, and this, in a natural way, induces a morphism between the underlying usual schemes. And what happens is that, of course, well, of course, it's quite clear that if we take the structure sheaf and mod it out by the ideal generated by the other elements, we obtain the structure sheaf of the underlying scheme. No? We obtain a natural projection, which, of course, geometrically means that we have an embedding of the underlying usual scheme into the superscheme. No? And this is something structural that we always have in all cases. But then what is a kind of subtle is if you have, you can ask if you have a morphism in the opposite direction, namely if this natural inclusion of superschemes has a retraction. And when it happens, we say that the superscheme is projected. And also, another notion, which is stronger, is that of split superscheme. That means that I mentioned already the Grassmann algebra. It means simply that you start with a locally free OX module, so a vector bundle on the underlying usual scheme, and you take the sheaf of sections of its exterior algebra, compatibly with the projection. Okay. And then you can say that X, here there's a different definition that I don't want to deal with it. You say that X is locally split if this happens locally. For instance, on the open sets of some suitable covering. It's immediate that a split, of course, implies a locally split. It also implies projected, basically because inside the exterior algebra, you have the structure sheaf of X sitting just as the degree 0 piece. No? So in a natural way, superschemes are projected, right? And the case when, now you see already the issue of saying what the dimension of a superscheme is non-trivial. There are several possibilities, and one, here I chose the easiest, namely to associate a dimension to the superscheme when it is locally split. I have a slide about that. Depends on the definitions, but the answer is yes, in a way, as we shall see. Super smooth, I mean, smooth as a super object. And then we assume that X is locally split, so locally we have a vector bundle which will be of rank n, and this number is actually, I'm assuming that X is connected, whatever, so this is a constant, the same in every open set, and so you have a pair of numbers. M is the dimension of the underlying scheme, and n is this vector bundle, which exists locally, the rank of this vector bundle. And so examples, just this is the first example is tautological. Now you start from a vector bundle, and you take the exterior algebra, and you get the split superscheme associated to E, vector bundle on the scheme normal X, so to say. If the vector bundle is this, of a projective space, you get what this was defined by Manning for the first time, as far as I know. You obtain the projective superspace of dimension Mn. And you can also construct in the same way the Grassmann, in some way Kmn, which is just the direct sum of Km plus Kn with the natural Z2 grading. You can consider the sub-supermodules of dimension AC, and you get an object whose underlying scheme is the product of two ordinary Grassmannians. And then you have, as usual, the non-trivial graded, the non-trivial structure sheaf, superstructure sheaf, so to say. No. So this is locally split, actually. Nice, it's a locally split with this complicated dimension. And as usual, there is a particular case where you get, in this case, a super projective space, or a projective superspace, as usual. And then, of course, to do algebraic geometry, you need to have a kind of zoo of morphisms of different kinds, and the usual definitions extend. So you can talk about separated, proper, faithfully flat morphisms. You can define fiber products, and after that, you define the fiber of a morphism. And then, for instance, what about, these notions, separated, proper, flat morphisms are exactly the same. The notion of smooth morphism is a little more tricky. There are different definitions, actually, which all coincide in the case that X is locally split. So to make it easier, we assume that X, the superscheme, is locally split. And then, for instance, you can assume that the differentials, the cotangent sheaf is a free module, locally is a free module of rank Mn, where Mn is the dimension of the superscheme. Or equivalently, again, in a locally split case, you have this thing. So if locally split, you have just a vector bundle and the scheme, and you want that the scheme is smooth. No? And okay. So this is the absolute case, right? The definition is about smooth morphism, and this is the absolute case over a field, so you get the notion of smooth for a superscheme, not for a morphism or superscheme. And now, actually, my talk is based on the fact that in algebraic geometry, of course, the notion of a projective scheme is very useful, right? And this generates the notion of ample line bundle, etc. And so we are accustomed to use this as a technique, right? Very often. And then you may think, okay, let's start with a definition of superprojective morphism of schemes. And this is the usual one. I mean, you define the relative proj of a symmetric superalgebra or supersymmetric algebra. You take the super spectrum of just taking homogeneous elements in the proper and appropriate sense. And here, I made the difference when M is locally free or not. Like Grothendieck, you can make this construction also when M is not locally free, just any coherent sheaf, and this may be useful. But when E is locally free, you get actually a projected superbundle. And then you can say that, as usual, a morphism is super projective if it factors through a closed embedding followed by the projection onto the base of a projective superscheme. And you can perhaps just be happy to say super projective when you have just a coherent sheaf playing this game, and say that the morphism is strongly super projective when the coherent sheaf is locally free. It's always in the graded sense, Z2 graded sense in the super sense. And then, of course, what happens is that the fibers of such a morphism are projective superspace. Now, what happens is that in supergeometry, there are very few super projective schemes. So to say, quotation mark, much less than you have in usual algebraic geometry, and much less than you would expect. The reason is the following. I'm not going to comment this slide. This would be for a more technical talk with more time. This is just the usual definition of ample, in particular of relative ampleness with respect to a morphism. The usual definition, mutatis mutandi. Mutatis mutandis. And then there's an interesting, so we have a notion of a very ample line bundle over a superscheme, and there is a result by these three people. Of course, since you have the canonical embedding of the ordinary scheme into the superscheme, if you have a line bundle on the superscheme, you can restrict to underlying ordinary scheme, and it happens that a line bundle on the superscheme is very ample if and only if its restriction to the underlying scheme is very ample. And then the following happened, that if X is projected, this is another story. When X is projected, since you have this map, any invertible sheaf on the underlying manifold gives a line bundle, gives a line bundle on X, just taking pullback, which restricts to this line bundle under the canonical embedding. And then you have the following, that if X is projective and the underlying scheme, the underlying scheme is projective, then the superscheme is projective as well. Particularly since we are dealing with the absolute case, it embeds into projective superspace. But in general, when the superscheme is not projected, there is no reason why this should happen. So the fact that the base is projective does not imply that the superscheme is superprojective. In particular, the Grassmannians, apart from some degenerate case, super Grassmannians are not projective, as was discovered by Penkov. And this, of course, is a signal that something is going on. Yeah.
I think B is DC in this slide.
Say it again?
B is C on that slide. Because you have B, and in Grassmann you have AC.
Yeah. Yeah, of course. Yeah, it's strange. Here there is no C. Yeah, thank you. Thanks. Yeah, indeed, even the previous formula was wrong. I corrected it. I didn't correct this. Thank you. Correct. Yeah. You have a good eye. Okay. So, we are in a situation where perhaps we might think we are going into trouble because we don't have enough super projective super schemes. And then the idea might be the following. Perhaps the property of being embeddable into a super Grassmannian might be enough to work. And this doesn't imply that the object, the superscheme, is super projective. So on one hand, we realize that there's a scarcity of projective superscheme. On the other hand, perhaps the embeddability into a super Grassmannian might replace the notion of being projective. Okay, this slide just gives the notion of a relative super Grassmannian. Just as we know, if you have a vector bundle on a scheme, we can take the Grassmann bundle associated with it. So you can do the same. I'm not going into that. You can also introduce flag super schemes. I'm not going to do that. And this is, on the other hand, a very nice result, I think. Namely, in a sense, super Grassmannian are not projective, but almost. Namely, they're always dominated by another superscheme such that when you compose the morphism from this X bar to the Grassmannian with the projection over the base, the composition is super projective. So they are not super projective, but they are in some sense dominated by a super projective object. So is this useful at all? Actually, I have 10 more minutes, right, Eduardo?
Yes, a little more.
So I have to cut. But anyway, the message is the following, that, for instance, So suppose that you want to study the representability of the Hilbert factor, right? So you define, the ordinary case, right, you define a functor which to any scheme associate the closed subschemes of this product, which happens to be proper and flat, because this is nice and this makes the theory work well. And then you discover that this is representable, no? This functor is representable in a suitable way. And then when you try to work this out, so in the super case, so you give the natural definition. Here really there is nothing strange to be done. You realize at some point you need to use embeddings into projective spaces. So what to do? And the problem is indeed resolved by that property, solved by that property of the Grassmannian. So you start studying this problem, you discover that this functor is a sheaf. Sheaf is a sheaf functor, or there's a risky topology of scheme. You do the usual thing, namely you consider, you want to consider schemes parameterizing a closed superscheme of a given Hilbert polynomial. Here, what happens is that a Hilbert polynomial is a pair of polynomials, simply because when you have a coherent sheaf on a superscheme, you take homology groups. These are naturally graded, and their dimension is a pair of numbers. And therefore, you produce in a natural way, you produce two polynomials. And then, for every choice of such a polynomial, you have a subfunctor of the Hilbert functor, right, where you just pick up the closed subsuperschemes whose Hilbert polynomial is this P. And therefore, the functor decomposes as a union of all these subfunctors as usual. And then, at first, you consider the super-projective case. So you start from or the quasi-super-projective, makes little difference. So you start from such a morphism. And then first you prove that when you fix the Hilbert polynomial, you have this functor is representable. You see the different font, no? Different. This is the scheme. This is the functor. And this is the scheme representing it. So you have this result, and then you realize that. The question is this? No. Is this proper over the base? The morphism is proper over the base. Usually you solve that by embedding the super Hilbert, the Hilbert scheme, sorry, into a projective bundle. And then since projective morphisms are proper, you get that the morphism is proper as well. And here this is not possible, but you can embed that into a super Grassmannian. And the projection of a super Grassmannian is proper. So we prove this. And then simply the whole functor is represented by the disjoint union of all superscheme representing the Hilbert functor with fixed polynomial, and this implies, for instance, good properties that this one, right? Note that here we have P, here we have no P. So we don't know if it is proper. Actually, you don't prove that because it happens to be, it doesn't happen to be locally of a finite type, but only of locally of finite type and separated. So this is what you get, which is what you expect actually. And then you go to the general case. Exactly with that property of the Grassmannian, because first you prove that if it happens that your X is dominating this sense, there's effectively flat morphism on top of it to some X bar, such that the composition from X bar to S is quasi-super projective, then you are done. Because you use your previous result in the super projective case to deduce that this functor is representable as well. And then you get to the same results. Particular that the super Hilbert scheme is locally of finite type and separated. And then you get that whenever X may be embedded into a relative super-Grassmannian, there exists a Hilbert superscheme, no? Because we have this property, and we saw that this property, the existence of this X bar, this happens for the super-Grassmannian. So we have this corollary. So this is very nice because to have a result that tells you that the Hilbert superscheme functor is representable when the morphism is just projective or quasi-projective is not enough. For instance, if you try to prove that the super Picard functor is representable, this is not enough. It's not enough to have the representability of the Hilbert functor in the projective case. It's not enough. This is enough. And indeed, in another talk, I could talk about the representability of the super Picard functor. And then, on the kind of reversing the situation, we can characterize, since to be embeddable into a super Grassmannian seems to be a nice thing, we might ask if we have a criterion to decide whether some superscheme or morphism superscheme is embeddable into a super Grassmannian. And then we have this result. If you have morphism, proper Noetherian, I don't know, it appears here, but we always consider Noetherian superscheme from the beginning. And then the following conditions are equivalent. So, yeah, the fact that X is a super Grassmannian embeddable, so to say, or that it is dominated by a smooth surjective morphism. In this case, if the morphism is smooth and surjective, it's enough to increase the odd dimension, so to say. So the relative dimension is enough, it is 0n. Or if the morphism is just, or we have that this happens when we have a faithfully flat morphism. Again, such that the composition is super projective. So this is a characterization of the superscheme of morphism of superschemes that are embeddable into a super Grassmannian. And I think this is the last slide. And this is indeed, this property in this proposition is used in the proof of the representability of the super Picard functor. Namely, you might ask, right, if you have two superschemes always working in the relative case, right? So two superschemes over a base superscheme, two superschemes X and Y over a base superscheme S, then of course you have a functor of isomorphisms, and you may ask if this is representable. And this is a very useful technique, something that you really need. And then you see this equation, this thing here shows exactly that this functor, no, is representable. No? This tells us that this is exactly representable. And this, for instance, used. The representability of the super Picard functor is also used in the construction of the construction of stable supermaps. In particular, not only of course, when you do stable maps, you consider punctured algebraic curves, Riemann surfaces. And what happens in the super case is that you have the usual punctures, so punctures of the underlying object. And this terminology comes from string theory. They are called Neveu-Schwarz punctures. But in the old case, you have also things that are called Ramon-Ramon punctures, and these are basically, it's some special structure along a fixed divisor. In the same way, if you want, as a collection of punctures in a curve is a divisor, when you have also a node dimension, you have also divisors with a node structure, and this induces the existence of other kind of punctures that are called Ramon-Ramon. And if you want to do things nicely, you need to take into account that as well. And for instance, if you want to prove that stable supermaps make up a decent object, a superstack, you have to prove, you have to use this result. And I think that with this, well, it's 12:40. Great, I'm over. Thank you.